Okay, so I've been slacking way too much with calc. So one video a day until I finish. How many are there? 32 videos. And I'm on the ninth. So yeah, let's get started then.
So from last time, we're still working on derivatives, and we've already done the derivative of 2x squared minus 3. Let's look at finding the derivative of something a little bit more complicated. Do you remember, firstly, what the derivative does for you?
Slope of a tangent line of a curve at a point.
Sure, slope of a tangent line, or in other words, slope of a curve at a point, right? And we've
Just
gone
slope of a
past
curve at a point, okay.
the stage of just finding it at a specific point. What we're doing is we're finding the formula for the slope. That way we can plug in any point that we want and find the slope at any point. Remember that? That was the last thing we were working on. So let's go ahead, let's find the derivative, which is slope of a curve at a point. Do you remember how to write the derivative of f of x, by the way? Good, f prime of x, and that looked like a little dash. So find f prime of x for f of x equals 2x cubed minus x.
Okay, let me try this on my own. So the difference quotient is f of x plus h minus f of x over h. So you have f of x plus h. We have x plus h. If you want to do slope, no, y's on top. So you have f of x plus h minus f of x over x plus h minus x. The x's cancel out, and h is left. Okay, we're chilling. So now I just plug that in. We already have f of x, so 2x cubed minus x. And that's in parentheses, so you gotta distribute the negative. Gotta find what f of x plus h is. I'll do that right. I'll do that right here. F of x plus h equals 2x plus h cubed minus. Gotta move this over. X plus h. 2x plus h, x plus h, x plus h, minus x minus h. Two x plus 2h, x plus h, x plus h, minus x minus h. 2x squared plus 2xh plus 2xh plus 2h squared. It's going to get really big. Times x plus h minus x minus h two x cubed plus 2x squared, or 2xh, be x squared h, plus 2x squared h, or I could combine these, plus 4x squared h, plus 2xh squared, plus 2x squared h. Gonna shrink this again. Plus 2 plus 2 x h squared plus 2, or what we could just say 4 plus 4 x h squared plus 2h cubed minus x minus h. So I'll look for similar like terms. I think these are this doesn't combine. 4x squared h, 4x h squared, that's different. Two x h squared. Oh wait. This should combine with this. Plus 2x h squared. 4x h squared, okay, that combines. Two h cubed doesn't combine. And these last two don't combine. Trying to make them different. So 2x cubed plus 6 x squared h plus 6xh squared plus 2h cubed minus x minus h minus 2x cubed minus x. It's all over, I'm not even gonna put it over h. I'm just gonna solve this. Okay, the x's cancel out. 2x cubed cancels out. And this should be good because every term has an h, so we can factor it out. Okay, let's cancel out. 6x squared plus 6xh plus 2h squared minus 1. Wait, this is as h approaches 0, not x. Six x squared plus these approach 0. Minus 1. Alright, so this is the derivative. And he's probably going to ask to find the equation of the line. So oh, no, we can't do that without a point. Yes, this is the slope of the curve at any point, because he didn't give a specific point, so we also can't find the equation of the line.
Basically, here's what our derivative said. It said that you can find the derivative, or the slope of a tangent line to a curve, or the slope of a curve at a point, at any point, by taking a limit, our fun limits that we have. Fortunately, these are a little bit easier than some trig limits we know about. As h approaches 0, f of x plus h minus f of x all over h. That's the idea. If we can fill those things out and work with it, then we'll have our function, or we'll have a derivative function. What I've told you to do is find f of x plus h and find f of x before you fill it out. Find that off to the side. So my question is, can you tell me what is f of x in our situation right here? We'll start easy.
2x cubed minus 6.
Good. Are y'all okay with the 2x cubed minus x, where that's coming from? So that's just our function. That's all we got to list down. Now we've got to go ahead and find the f of x plus h. F of x plus h says, do I just add h at the very end? Is that the appropriate thing to do? No, it's like x plus h. It says you can't separate that thing. So tell me, what is f of x plus h?
2x plus h cubed minus x plus h.
Okay, good. So everywhere we see the x, we're going to insert that entire x plus h. Do you remember doing that also? So it'll be x plus h to the cubed minus, so it does have to be x plus h in that as well. So everywhere we saw an x, we're now putting x plus h in parentheses. Okay, show of hands, how many will feel okay with that so far? Now, we're about ready to go ahead and substitute this into our function. Just make sure you do one thing. Remember that what this says is you're subtracting f of x, right? subtracting the whole thing. So if you're subtracting that whole thing, what do I need along with that 2x cubed minus x? I need something with it. Because that minus is going to distribute and change the signs. Are you with me on that? If I do it just like this, this is good, this is great, this is bad, that's real bad. Why is that bad?
No parentheses.
Yeah. This says I'm subtracting 2x cubed, but I'm not subtracting the minus x. This would say the appropriate thing for us. That would say. Do you see the difference there? Or do you see why we need that? We're subtracting the entire function f of x, subtracting the entire function f of x, and then putting it over h. Now we're going to do some fancy algebra. You need to know how to distribute x plus h to the third power. If you ever heard of Pascal's triangle, this will work for you. Have you heard of Pascal's triangle before? That's the way that you can expand this two-term or binomial expansion to any power that you want. I guarantee you that this is going to be without doing much work, because you need to FOIL that out, right? Just a couple times. I won't do the 2 yet. I'll do the x cubed plus 3x squared h plus 3xh squared plus h to the third power. Guarantee it's like that. If you want to learn how to do that with Pascal's triangle, come and see me or look that up. It gives you the coefficients, 1, 3, 3, 1, for every row of Pascal's triangle. That's how you do that. Minus 2x cubed plus x. Oh, no, I forgot something. So I've just done this little part. That's all I've done. What's that going to be when I'm done with that?
Minus x minus h.
Okay, and then minus 2x cubed and plus x. You see where the plus x is coming from at the very end. Minus and negative, we're going to be adding that ultimately. Okay, last little bit, if we distribute that 2x cubed, we'll do that next time. We'll go ahead and stop there. I'll talk about how to finish this up later. Okay, so we're working on a problem. We're trying to find the derivative, which is, what's the derivative again? Thank you, one of you. Where's my applause now? Yeah. No. Slope of a curve at a point, folks, is what a derivative is. That's what you need to know. So every time I ask you that question, what's a derivative? It is the slope of a curve at a point. That is what you're finding here. Did you get me?
Is it a formula?
We're finding the function of the slope right now, yes. We're going to find it in general. So we've made it down to this far. We have our difference quotient, and that means the slope. The difference quotient basically just gives you the slope between 2 points. We're just allowing those 2 points to come really, really close together. That's why the h goes to 0. It says that distance between the points is shrinking. It's collapsing to 0. And that's going to give us a slope not at 2 points, but at 1 point, which is, in fact, a tangent line. We've done the difference quotient f of x plus h. There we go. F of x, we've plugged that in, we've worked it out, and now we're going to see that everything except for terms that have an h in them, pretty much have to go away. Because if they don't, you're not going to be able to factor that h, and you're not going to be able to cancel out that h, which is exactly what you want to do. Let's see if that happens here. Do all my terms that don't have h in them disappear?
Yeah.
Geez, I hope so. Well, let's see. Does the 2x cubed go away?
Yes.
Gone. How about the x?
Yes.
Yes. That's everything that doesn't have an h. What that means is that you should be able to factor out an h from the rest of it. If you can factor out an h from the rest of it, you can have h over h. That's something we can simplify. You get me on this? So I'm going to work over here. This gives us a limit. H to 0 of, would you mind if I factored out an h as we went? You okay with that? So I'm going to factor in h, this is our remaining terms. This negative h, 2h cubed, 6x h squared, 6x squared h. So I'm going to factor out the h and get 6x squared plus 6x. Do I still have an h here?
Yeah.
Okay, good. You need to see that. Plus 2h squared.
It's not cube.
Oops.
Or is he combining something?
minus 1. Raise your hand if you're all right with that so far, the fact.
No way, I got that.
Cool.
Is that 6x squared? Oh, he's factoring. Okay, already.
Reason why this works, now you have the h over h. As soon as you can factor, you can simplify that out. You can't do it before then, but now we can simplify those h's away. Are you
Right, that is exactly what I got, right? 6x squared plus 6xh plus 2h squared minus 1. Nice.
now able to plug in h equals 0 and get something out of it? Sure, let's do it. What happens? Do I still have a 6x squared? Yeah. Yeah, that doesn't have an h attached to it, so 6x squared is right there. How about the plus 6xh?
Here's a way.
That's 0. Why is it 0?
H approaches
Yeah,
0.
you're really doing this. 6x times 0, because h is 0. Plus 2 times 0 squared, because, well, h is 0. How about the minus 1? Do I still have that? Yes, absolutely. So this is going to be your first derivative, we call it the first derivative, 6x squared minus 1. Okay, now, test you on what I said 2 seconds ago. What did we just find?
So called curve. Any point.
Right, exactly. Whatever you mumbled, you're right. Sure. Yeah, we found this. I think I heard it from like 10 of you, maybe all of you if you were doing ESP or something. We have the slope of this curve. Where?
Any point.
Wherever I want. Yeah, wherever I want it. If I say at x equals 3, you can find it at x equals 3. No, I'm not going to. I'm not going to, but we could do it, right? If I said find it at x equals 3, how would you go about doing that? You'd plug in 3 to this. That's going to give you the slope, just the slope. Are you with me? You'd plug in 3 to this to actually find the point. Do you follow me on that one? So if I ask you find the equation at x equals 3.
So, I'm not going to write this down. But you'd plug in to find the slope into the derivative that you just found. And that would be 9 times 54, 53. So the slope's 53. Then to find the y value, you gotta plug into the original. So 27 times 2. Wait, what is 37? 54 minus 3. So, I will write this down. 351 is the point. What did I say the slope was? 53. Y minus 51 equals 53. X minus 3 minus 51 equals 53x minus 159. 159 minus 51, 108 minus 108. I guess that's it. Could be wrong, but
The slope is going to be f prime of 3. The point is going to be 3 comma whatever you get when you plug in that point. In our case, if I plug in 3, tell me what I get when I plug in 3.
27.
51.
Oh, well. That is what I got, right? Yeah.
The slope would be when I plug in 3 here. If I do that, I'm going to get
53.
53. Is right? Okay. that would be my, do you see how we're getting the, I went quickly through that. Do you see where we're getting the point from? The point comes from my original function. That's what gives you points on your graph. The slope comes from your derivative function. So you plug that in, we find the slope. You can now use point slope and figure out that equation very easily. It'll be a straight line. All your tangent lines will be straight lines. How many will feel okay with this example? At least get as far as the derivative. All right. Would you like a couple more examples?
Yes, sir.
Yeah.
Yay! Fantastic. What a good Friday. All right, well, more examples. First example is this. You're going to find something out kind of interesting here.
All right, my bad. I was looking at something.
Now, we're actually going to do a little critical thinking about this. Could we use this whole shebang, this whole limit thing, to find the slope of that?
I mean, you could. I think I remember this from before. 3x plus 2 is it's a straight line. So you already know the derivative is 3x plus 2.
Because this stands for slope, right? Could we do that to find the slope? However, look at that. What is that? Yeah, that's one of these. What's one of those? A slope-intercept, that gives you a linear equation. Could you look at this and tell me what my slope is here? What's my slope?
3.
Then I guarantee you, if you were able,
Oh, I
if you
guess
were
the
doing
slope's
that,
3, not 3x plus 2.
your slope is 3 no matter what, because that's a constant, right? That slope doesn't change at all. That's a straight line. Without doing any work at all, I know that the slope, or my first derivative, is going to be 3 from that function, because the slope is 3. What I'll write out for you here is, if you have any slope-intercept form of a line, don't waste your time doing that. You need to know what you're doing by finding a derivative. What are you doing by finding a derivative? You're finding the slope of a curve at a point, right? What's the slope of this curve?
M.
At any point? Because lines don't change. Slope of that curve is m no matter what. So for any y equals mx plus b, slope equals m. It's a constant. It doesn't change. It's a constant, it doesn't change at all. So with any line, that's pretty easy. We don't have to do that formula at all. We just know that the slope of a line is that m, that number, that coefficient of x, which is pretty cool. So the slope of any straight line is just m. That works for our derivatives as well. Okay, let's deal with one that's, I just want to show you that. So if you got that on your homework and you're like, wow, I could do all this stuff. No, if you get a straight line, just take the derivative and that's just a slope. It's a shortcut, I guess. But not really a shortcut, you already know what slope is. I'm just telling you that derivative means slope, right, for real. So if you know what the slope is automatically, that is your derivative. Don't waste your time. Now, how about this one? Here we will use this because the slope of a line is always constant. Is the slope of this thing constant? Is that a straight line? Do you know how that looks?
Is it the V?
It'll do like a dance move.
No, that's...
Yeah.
Wait, is that like the, like that? Yeah, close enough. Not really. Okay, yeah, that wouldn't be constant.
Maybe like a disco. We'll do exponential later. I didn't do disco, so I'm not that old. That was my best disco impersonation. Anyway, let's go ahead. Let's find the derivative and the equation for the tangent line at x equals 4.
Okay. Conjugate. We don't want to distribute on the bottom. X plus h plus x square root x plus h minus x wait, hold on. Okay, those would cancel out. Minus x. Wait a minute. One? No, that can't be. It's not constant. see what he gives.
Give it a try.
Wait. At x equals 4. Alright, let me just try that then. Can you not solve for any point on this? Oh wait, I forgot the— no, you can. I just forgot the thing at the bottom. Oh, no, crap. Let me try that again. X plus h plus that minus x h times x plus h. This is wrong. Plus square root of x here. This is what I should have gone. Cancel these out. 1 over square root of x plus h, or plus just x actually. 1 over 2 square roots of x. Since we're looking for 4, we can plug in 4. 2 1/4. And that's the derivative. So we got that. And we're looking for the equation too. Pretty sure? Yeah. So for 4, 12, 14, well, that'd be 14. So we know the slope for this point. So plug this in the point slope. Y minus 14 equals 4, or 1/4. X minus 4. X over 4 minus 1 equals y minus 14. X over 4 minus 13, or no, plus 13. And to make this better, actually, I'll separate the slope so you can see it.
First thing we got to do, of course, well, in order to find the derivative, this is not easy like our lines, all right? We can't just look at that and go, oh, the slope is, we don't know, right? We don't know. So we're going to have to use the formula for the derivative, for the slope. So in other words, we're going to have to fill out this thing. Why don't you try that now? Go ahead and give it a try. Remember how we do it is we want to find f of x and f of x plus h, the non-separable x plus h, separately, and then plug them in. Go ahead and try that. Shouldn't take you long for this one. By the way, you can do this one of two ways. You can plug in a specific value for x if you'd like to. What I prefer you to do is do the derivative in general. So this is a secondary question, okay? And the equation of the tangent line, I want to find the derivative first. What we're most worried about right now is finding the function for the derivative. Do you get me on that? So please, if you plugged in 4, just erase that, put the x. I want the formula for the derivative, and then we'll be plugging in that point. Do you understand the
Good
difference
thing I
there?
found the
So
formula.
we're finding it in general. That way, if I give you a different point, like x equals 5, you don't have to redo all your work, because that'd be lame. If I asked you for like 10 different tangent lines, you don't want to do this 10 different times. You want to do it once, and then just plug in 10 different numbers. That's way quicker. You see the difference? That's what I want from you. So here, for f of x plus h, I'm going to have the square root of what? Square root of x plus h or x plus h? Hopefully like that. F of x, well, that's just square root of x. Did you get those two things correct? Now we just have to substitute those into their respective places. So this is going to give us the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. So all those limits that I gave you where you had square roots minus something else wasn't just arbitrary, because now you're seeing some of the techniques that we use for our limits from the last couple chapters. Remember that? How do you get rid of that? Conjugate. That's why we did that. Are you going to distribute the top? Yes. Distribute the bottom? Heck no. You're trying to get rid of the h. So this wasn't just useless practice we were doing. That's why I made such a point of this when I went over a couple things with you, that these parentheses you're about to put on here aren't meaningless. Remember me talking about those parentheses? Oh, please nod your head. Do you remember me talking about parentheses? Good, because hopefully I wasn't just talking to a wall. We need parentheses because we're multiplying this factor times that entire expression, which lets us ultimately cross some stuff out and simplify it. Okay, now you're going to help me out with this. I know I still have a limit as h goes to 0. When I distribute the numerator, which I do have to do because, listen. What you're trying to do is get rid of the radicals up here, right? Wherever you're trying to get rid of the radicals, that's what you distribute. Should I distribute the h? No. I'm not trying to remove any radicals from right there. So whatever you're trying to rationalize, that's what you distribute. Whatever you're not trying to rationalize, that's what you're going to try to cross out ultimately. If you were to distribute this now, you'd have to refactor it later. You don't want to do that. You want to leave it the way it is so you can cross the h out. That's your whole goal, cross the h out. So we're going to help me out here. Okay, I get the x plus h. I get the x because square root times itself gives you the radicand, and that's the part inside the square root. We're going to get plus and minus the same exact thing. Do you see it? What's last? Minus x, right? All over. Don't distribute that. See anything nice that happens?
Cross out the h. X is.
They have to. They have to. The only thing you can have left up there is something with an h that you can factor out and cross out itself. Otherwise, this problem falls apart. So those x's are gone. Okay, what now? I like the h's going away. What do we have remaining then?
1.
Good. We don't just have this part, right? It's under 1. So that becomes a 1. Are you okay to plug in the h? Wait a second. The h is still in the denominator. Is that okay?
Yes.
Sure, because when I plug it in, I get x plus 0. That's fine. That's still x. That's still something. So here I have, after I plug in the h, I stop writing the limit. I have 1 over the square root of x plus 0. That's the square root of x. Plus the square root of x. Can you make it that far? You all right with that? Can I put those together? You get 2 root x. 1 over 2 root x. Show of hands, how many people feel okay with our derivative? Feel all right with that? Good. Remember when you add root x plus root x, you don't get x. You get 2 root x. Okay, that's not what gets rid of its multiplication, that does. Now we're almost done. At this point, we've got to use slope-intercept. I'm sorry, point-slope. We need a point and a slope to find the equation of any line. So we need 2 things, point and slope. Do we have a point? Really?
Nope.
We have an x. How do you get
Look
the
at
y?
the original.
Because right now we need the slope,
Original function.
which is, I don't know, and we need a point. I can tell you the x-coordinate. The x-coordinate for the point is? 4, okay. How do you find the next part of that? Wait, plug it in here?
No.
What's this again?
Slope.
That's slope. Good. What gives you points?
Your original function.
Where am I? Right there. That gives you points. Plug it in here, this will give you points. So plug in 4 here, what do you get? So this is the point 4,2.
How did I get? Wait, what? I get 14. I actually have no idea how I got that. Jeez. 2, 2, 1, 1. Okay. That was weird. I don't know how I got that.
Are you okay with that? Remember, our function was simply the square root of x, right? Square root of x says if I plug in 4, I'm going to get out 2. That gives me the point. Now, this thing should give you the slope. Don't plug this into point slope form. That'd be ridiculous. You want a number to plug in. So if I were to plug in 4 here, what's that going to give me, please? 1/4. Very good. Because square root of 4 is 2. 2 times 2 is 4. That's 1/4. So f prime of, oh, it says f prime of x even. That's kind of nice. What's your x? Your x is 4. Plug that in. That's 1/2 times the square root of 4. Okay, I need to know, are you okay on finding the slope? Nod your head if you are. And the point? You see where those things are coming from? Hey, plug them in and give me slope intercept. So go ahead and do that if you haven't done that already. I even gave you nice points. What a nice guy I am today. Just today. Monday, back to the same old guy. Okay. Y minus 2 equals 1/4 x minus 4. Distribute y minus 2 equals 1/4 x minus 1. Add 2. Y equals 1/4 x plus 1. That's it. That's it. What's interesting, what's kind of neat about what we're doing here, this curve is kind of crazy, right? It does this. It's half of a parabola on its side. What that line will do if you were to graph it, if you graph both of them on your graphing calculator, that's going to make the half parabola on its side. This is going to make a straight line intersecting the y-axis at 1 with a slope of 1/4. It will guarantee to intersect this curve. Now it'll intersect it at exactly x equals 4 at the point 4,2. At 1 point only. That's kind of neat, right? So could you tell me what's the slope of this curve at the point 4? It's 1/4. What's the equation for the tangent line? It's right there. Slope of 1/4. How many people feel all right with that one? Good, all right. We're going to do one more example, and then I'm going to tell you a little bit more about this idea of derivatives, where you can take them, where you can't take them, and why. And so a little bit more theory. So one more example, application action. Do you remember what instantaneous velocity was?
Velocity is given point.
Instantaneous, though. Average velocity would be between 2
Be
points.
exact. velocity at
Someone said it, what was it?
point.
It involves a limit, right? In fact, an instantaneous velocity was
It's not
simply
the
what we
average,
found out
it's the opposite.
is a derivative. It was a limit of the slope between 2 points. It said instantaneous, said a slope of a curve at a point. That's what it was. In fact, we had basically the same thing with a t instead of a x, where f was the position curve. Does that look familiar to you? That was instantaneous velocity, and I gave it to you a while back. Well,
So
if
it's
this is
the,
true,
difference
notice
between-
that all this is equal to the first derivative of your f, right? That's what that formula is. What that says to us is that if this gives you instantaneous velocity, and this is simply the formula for the first derivative, velocity is just, and now we can say it for real, velocity is simply the first derivative of a position function. Now, we might have known that just from this, but now we can say it for real. So this is instantaneous velocity, which is denoted v of t. Instantaneous velocity is simply the first derivative of a position curve. Instantaneous velocity is the derivative of a position curve. Let's do one example just to flesh it out a little bit. Do you know anything that's 1,250 feet tall? No, that's 5,000 feet tall. Sure, let's say that.
110 stories.
110 stories times 10. Yeah, that's about right. So let's say this is the Empire State Building,
How much?
and you're up.
How many feet is a story? $14. So this be like 9 stories. Or what? No, if one is 14, this could be like 90. Yeah, like 90 stories or something. And a little smaller.
There, and you're with someone you really don't like, ex-girlfriend, whatever, and you just go, okay? That's what this is. No one likes ex-girlfriends. Just kidding, joking. You wouldn't ever push her off the building, right? Besides, there's fences up there. You couldn't do it even if you wanted to.
You'd have to throw her.
That'd be 1,258. Anyway, just joking. This is about the effect of gravity if you just kick something off a ledge. That's what this is saying. So your position is starting at 1,250 feet, and you're just going to throw something off, and it's going to fall. That's what negative 16t squared will do for you. Does that make sense? In a vacuum. No, we're not living in a vacuum. This would be in a vacuum. I want to do 3 things. I want to find the velocity, the instantaneous velocity, the formula for that. I want to find out when this hits the ground. I want to find out what's the velocity when it does hit the ground. So 3-part question. So first part, find v of t. Second part, when hit ground. Third part, how fast? How fast hit ground? That's our questions. Can you please tell me how you're going to find the velocity of that position curve? What are you going to do right now? You're going to take the derivative. Why don't you
50 minus 16 t plus h squared. 1250 minus 6, minus 16 plus h, t plus h, t squared plus th plus 2th plus h squared. 50 minus 16t squared minus 32th plus minus 16h squared. $12.50 minus 16t squared minus 32th minus 16h squared minus 1250 minus 16t squared plus 16t squared. Let's cancel out. Cancels out. You have 32th minus 16h squared for h b prime of x factor out an h. So the limit is going to be negative 32t, which means the derivative is negative 32t when what hit the ground see, you do like 1250 minus 32t equals 0. Because you have your slope. Or would you set the original equal to 0? Well, hold on. That would be of t, I guess. V of 0, you just set the function equal to 0, wouldn't you? No, this is okay. When you plug it in like that, you're finding before the object starts falling. So no, that wouldn't be right. Zero equals 1250 minus 16t squared. So it'd be like 8.8388 or something seconds. I think position time graphs are usually in seconds. No, this definitely would, because you're falling. Sounds about right. How fast you'd find the derivative for 0. Or wait, no. You'd plug in 8.8388. It's 32. Gonna move this. Negative 32 times 8.8388. And this would give the velocity for hit the ground. So yeah, this is good. -8.8388. -282.8416 meters per second. Or this is in feet, so feet per second. Alright, let's see if that's right. A, B, C.
Go ahead and do that. Take the derivative for me. You already know all this stuff to take a derivative, so take the derivative of that thing. Velocity equals the first derivative of your position curve, in this case s. So s prime is velocity for you. That's how you would signify that. I'm going to start working on it slowly. Keep working on your papers. Let's see if we come up with the same thing, okay? I'll do it step by step, but I'll go real slow.
Crap. What does S tier stand for? Position at time t. Oh, displacement equals s. Really?
That's a square. Sorry. Horrible. Have you noticed that a lot of this is just algebra work? You notice that? Mostly just algebra. And you're like, dang it, I passed algebra. What the heck, Leonard? Give me some calculus. Involves algebra. Okay, by show of hands, can you raise your hand if you made it down to this far for me? Did you make it there? Good, okay. If you made it that far, you have the understanding for calculus down. You have the
Nice.
understanding how to use that formula down. The rest of it is just your algebra work, distribution, combined like terms, things like that. So in our case, for us,
So I'm basically done.
keep on working if you want to.
I'll pass.
Hopefully you saw why those parentheses were important, right? So if you don't have them, your 16t squareds are not going to go away, and you need them to go away. So if ever you come up with something where you're like, man, I'm not able to factor out an h, you've probably made a mistake. Go back and fix your mistake. That's probably what happened. Did you make it that far? Did you? This side? Yes, good, all right. This side? Does all the good stuff happen? Like it's supposed to? Everything besides an H goes away? Okay, well that's gone. That's gone. I see only two terms. Each of them has an H. Let's factor the H. Negative 32t minus 16h. Remember, I'm not so caring whether you factor out the numbers. I don't care, because you're going to be multiplying them anyway in just a second. So all I really care about for you right now is getting rid of that h. That's the key here, because that lets you take the limit as h goes to 0. If you do that, tell me what my velocity curve is equal to.
32t.
What happened to the negative 16?
Times 0.
How many were able to find that? Good for you, that's
Raise
fantastic.
my
You got
hand
that,
right
you got the derivative down. That is the instantaneous velocity at any point. So right now we've answered v of t. It is negative 32 t, where t is the time. That's right. T is the time. And we'll say, I think this is in seconds. So yeah, gravity should be in seconds. So this is in seconds. Next question, when's it hit the ground? Oh. When does something hit the ground?
0.
When the position is 0. So when does this pen hit the ground? If this was like a y-axis, I start at
Y equals 0.
6
Y
feet
equals-
and I drop it.
Or
It's the ground after it reaches a height of 0, right?
By or
What gives
X
you
intercepts.
height?
Huh? Where it crosses the Y. So it'd be X intercepts. Yeah, it'd be the X intercepts.
The first derivative or the actual function? The function does. So we want to know, when does this thing make 0? That's the question. You've done that since your introductory to algebra class. You want to find out, well, when's it going to hit the ground? When does 1250 minus 16t squared equal 0? When's the height equal 0? That's what you're asking here. Do you see that that's the height, right? When's the height equal 0? Find that one out. Oh, come on. You got this. Solve for t. Solve for t. There's nothing fancy about it, just get t by itself, which means you're going to probably either subtract 1250 or I would choose to add 16t squared to both sides. Next step, you're going to do what?
Add 16. Both
Divide by
sides.
16. You have a simple t squared. So divide by 16. What's 1250 divided? I can't do that in my head. How much is that?
78.1225.
78.1, 78 and an 8?
Yeah.
Get rid of the square. How do you do that? Root. Sure. Now, what do you have to do when you take a square root? Yeah, you typically would. However, we're dealing with time, right? So is a negative square, is that going to work for us, negative time? It happened in the past, man. Crazy, no. When you're dealing with actual time, yeah, technically you'd put a square root, right? But we don't have to do that because we're always moving forward in time. So we're just going to leave the positive, not the negative. Take the square root of 78.125 for me. 8.84 what?
Well, that's rounded, 8.388.
8.38?
8.3.
Okay, 388. So
388.
however much you want to be accurate here, you can be even more accurate here, just so you know, because you're going to be plugging that number in just a bit. So you said 8 point, let's do 39, okay? You said 8.388?
No, 838. 838.
Oh, geez. I don't have a calculator in front of me. 8.838?
Yeah.
Let's do 8.34 then. That sounds good. All right, very good. Seconds. Because I'm assuming this is in seconds.
I forgot
So,
that.
when will it hit
No,
the ground? It's going to hit the ground after 8.84 seconds. How fast is it going when it's hitting the ground? Well, this is a combination of these ideas. Do you know when it's going to hit the ground? Do you have a formula for telling you how fast something goes at an instant of time? Right there. If you want to find out how fast it's going when it hits the ground, you now have a function in terms of t and you have a t. Plug it in. It'll tell you how fast it's going when it hits the ground. It'll also give you the direction that it's going when it's hitting the ground. Not shortly after, because it's going to be stuck, but just before. So how fast? That would be v of 8.84 seconds. That's negative 32 times 8.84. Keep in mind, This is like neglecting the terminal velocity thing. This would be like in a vacuum, okay? So how fast is that going?
282.88.
282?
180 feet per second.
Negative, I'm assuming.
Yeah, negative
Negative.
feet per second.
288?
Yeah, 282. 282.
Man, they can't get the number right.
That's pretty fast. That says it's falling at a rate of 282 feet per second at the moment that it hits the ground. If you were some sort of an engineer, we'd have a little bit more complex of a thing here, depending on what you're dropping. You'd have wind resistance and stuff like that. But you probably calculate a basic structural integrity. If something's going to fall off of a 1,200-foot ledge and hit something, you're going to calculate so it withstands a forceful impact of up to 282.88 feet per second on top of that roof of your cab or
Pretty
something
cool.
like that. If you're working on a ledge, rocks drop off or whatnot. Did you get the idea? So that's our idea. It's kind of useful stuff. Pretty cool. Can't do that normally. Only with calculus and limits can you actually find an instantaneous velocity. So Nito torpedo. Next up, the next thing we got to talk about, we've been taking all these derivatives. We need to discuss when you can actually take a derivative. That's called differentiability. Can you say differentiability for me?
Differentiability.
Very good. Differentiability. So differentiability basically means the ability to take a derivative at a certain point. It is also a great way to score a whole bunch of points on Scrabble. Words with friends is too long of a word, so you can't win with that, but Scrabble. Now here's the idea. In order for a derivative to exist, which means it's differentiable at a point, this has to work. In order for a derivative to exist at a point, this must exist.
Alright, pretty basic so far.
In order for a derivative to exist at a point, this thing must exist. Well, that should make sense. You have to be able to take the derivative, right? And the derivative would mean working out this formula, because that is the formula for our derivative, true? However, notice that it's also a limit. Limits exist if the limit from the left equals the limit from the right. True? That's what limits mean. Limit from the left equals the limit from the right. Those things go to the same spot. We're not talking about continuity right now, okay? We're talking about limits. They match up the same spot. Whether it's defined at that exact spot or not, doesn't matter for derivatives, or sorry, for limits. It says it has to match up. So that must exist. Here's two implications that we have. Two implications. First one, let's say I'm talking about this specific point, that we'll call it right now a sharp point. Okay, we'll call it a sharp point. Do you understand that what this limit gives you is actually the slope of a curve, true? It gives you the slope. But for the limit to exist in general, the limit from the left has to equal the limit from the right. You believe that as well?
Yup.
What that means for us in this context is the slope from the left, because this is a slope, right? That's a slope. Keep that in mind. That's a slope. It says for this limit to exist, for this slope to exist at a point, the slope from the left has to equal the slope from the right. Do you buy into that? It's a limit. The limits have to be the same, but these limits connotate a slope. It means a slope has to match up. Look what happens. What's the slope doing as we're getting to this point? That's positive, 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 positive slope, right? But from the right-hand side, that's negative, negative, negative slope.
Yeah.
Are those slopes the same?
Nope.
Then that limit doesn't exist, because the limit from this way and the limit from this way, according to our slope, doesn't happen. The limit of the function, yes, that does exist. The limit of our slope doesn't exist. The slopes are not the same. Remember, we're not just taking the limit of the function itself. We're taking the limit of the slope. Do you see the difference? I'm not talking about whether the function itself meets a point. Yes, of course. The function meets up. The limit for the function exists. Does the limit for the slope exist?
No, different slopes.
No, that would mean the slope from the left is the same as the slope from the right. Is it? No. That means that at any sharp point, our limit will not exist, therefore we can't take a derivative at that point. I see some blank looks. Are you guys okay or no? Are you sure? Not really. Let me show you the difference between limits of slopes and limits of functions themselves. This is a function, right? Does the limit of the function exist here? Absolutely. Yes, the limit of the function exists. However, does the limit of the slope of the function exist? The slope is what we're talking about. The slope this way is going here. The slope here is a constant. Are those the same at that point? Then the limit of the slope doesn't exist. That's the difference that we're talking about. A derivative is slope, not a function itself. It's the slope of the function. So this says the slope is no. Those don't match up. Those don't make the same exact slope at that point. So our two implications are, number one, you can't take a derivative at a sharp point. At a sharp point. Why? F prime of x is a two-sided limit. It's a two-sided limit that gives you slope. If the slopes don't match up, the limit doesn't exist. If the limit doesn't exist, you can't take the derivative. That's the idea. The limit of the slopes don't exist. You can't take the derivative. Other one is this one. We'll try to be real careful. There. We're talking again at this point. At that point. Do you see how this, let's pretend it's barely a function, okay, barely, but at one point the slope would be vertical. Do you see that? At that one point, look what happens to our slopes. Remember we're talking about limit. Limit has to exist, means the limit has to be the same from the right and from the left. Here we're going to, oh, check it out, positive infinity, right? Here we're going negative infinity. Is positive infinity, negative infinity, same thing? No, no, the limit doesn't exist there as well. So two implications are you can't take a derivative at a sharp point or where the slope is undefined. Slope is vertical. This one, this gives at least two different slopes for that point. This one we're undefined. We're positive and negative infinity. Your slope is vertical. You can't take a derivative of that. How many people feel okay with our two implications here? All right. Let's see if you really understand it with one quick example. Is absolute value of x differentiable everywhere?
Sharp point.
In fact, if you get the limits of the slope, you'd see this. The slope is -1. True. The slope is +1. As you get to this point, the slope is still -1. The slope is still +1, right? Is -1 equal to +1? Then the limit of the slope can't possibly exist. This is not continuous everywhere. No, sorry, not differentiable. Not differentiable everywhere. The question also is, though, could you take the derivative here? and here, and here, all the way up to get that point, and all except for that one little point. Yeah. So what we're finding here are just the points where the function is not differentiable. Everywhere else will be fine. So I'll make a little note for you. These functions are not differentiable only at those specific points. These functions are non-differentiable only at those specific points. Okay, real quick question, a couple more pieces of information. We're almost in another section here. So last little piece of information for today. Firstly, we're going to talk about continuity and differentiability and how they have an interplay here. First question is, I'm talking about this point and this point. Is this function continuous at
No.
point C? Is it continuous at point C? Fails continuity. Therefore, is it differentiable at point C? No, the limit clearly does not exist from both sides. If it's not continuous, listen carefully. If a function is not continuous, it cannot be differentiable at that point. If a function is not continuous, it is definitely not differentiable. I'm abbreviating here, continuous and differentiable, okay? If it's not continuous, it's not, there's a long word, I don't like to write. So if it's not continuous, it's not differentiable for sure, you agree? So the next one, is this continuous everywhere? Continuous. Yeah. Because you don't get your pencil off the paper. Continuous? Is it differentiable everywhere? No. It's not differentiable right there. So just because a function is continuous doesn't necessarily mean it is differentiable. So that's not always true. Here's what it does mean. If a function is differentiable, it is definitely continuous. Differentiability is stronger than continuity. This is continuous but not differentiable. Everything's differentiable, it's automatically continuous. So if a function is differentiable, it is continuous. If a function is differentiable, it is continuous, for sure. The opposite I just told you is definitely not true. If a function is continuous, it does not necessarily mean that it is differentiable. I had a point. Okay, we'll end with there. We'll talk about endpoints next time, and I'll give you some different representations of how to make the notation for a derivative. How many going to sit there? You okay with it? You got it right? Is it love? Right, anyway. So we're talking about how to do these derivatives, and we talked about continuity with, that's the last thing we did, right? Continuity versus differentiability. We said if a function is continuous, it's not necessarily differentiable. It has to be continuous and have no sharp points, and then it will be differentiable everywhere. If a function is differentiable, that certainly means it's continuous, though, for sure. So that differentiability is stronger than continuity. You can be continuous without being differentiable, but you can't be differentiable without being continuous. Also, if something is not continuous, it is certainly not differentiable if they have a jump. So jumps and sharp points are non-differentiable. Now, the last thing I need to tell you is that I know I've given you a derivative is typically represented like this. That would be the most our introductory derivative. We do f prime of x. You guys have seen a lot of that before, right? Most of the time we write that. However, there's also some other things that we can write. We'll also write to find the derivative, this d dx. If you've seen that in your book, that's what it stands for. So d dx says, I want you to differentiate the function with respect to x. Basically, you think of it that way. So this says find the derivative or differentiate whatever function I give you with respect to that variable, a derivative with respect to x, of f of x. It means the same thing as doing that, right? The same exact thing. You okay with that one as well? You can also represent it, y, if you had a function y, you can write y prime. So y prime would also be a derivative. Or you can write, for a function y, dy dx. So this would be a derivative of y with respect to x. Same basic notation as this. So we have a function notation, and we have like our y notation. We have f prime of x or y prime. We have df dx or the ddx of f of x, or we have dy dx. They all mean a derivative. Basically, yeah. You probably stick with one version for a problem. So if I actually find ddx, you'll stick with ddx. If they find f prime, you'll just use f prime. But you need to know that when you see it. It's not something confusing. It's just a derivative there. You okay on that so far? Also, we can evaluate derivatives at points. We've done this. Find the slope of a curve at a point. You plug in numbers, right? And they can tell you to evaluate derivatives at certain points. How that will be shown is this. If you wanted to find the slope of a derivative at a certain point, it would be shown like that. Find f prime of a, where a is like 3, or -2, or you just plug in a number. That's how they would tell you, I want you to evaluate the first derivative at that specific point. This one's a little different. It would say, I want you to evaluate the first derivative at a specific point, but they do it like this. They'll put this long vertical line, and they'll put x equals a. I know it looks a little weird, right? But it just says, I want you to evaluate this. It's not, I made it long so you see that it's longer than normal. It doesn't have to be that. Well, it's certainly long, right? But this just says, evaluate your first derivative at x equals a. It's the same exact thing as this. These all mean the same thing. You could do this, y prime of a. Or lastly, you could do dy dx at x equals a. That just, this long line just means evaluate. I'm going to go with our symbolic notation for this. So this is our evaluation. This is just a way we represent our first derivative. And that pretty much wraps up section 2.1. That's it. So if we get the stuff down as far as the continuity goes and finding derivatives, we're good. Do you have any questions before we move on? All right. Well, I've done for you all the the theory stuff behind derivatives. I've worked them out for you. I've showed you how to get them. I went from finding the slope to taking the limit of that slope and moving the point really close to another point, saying this is a tangent line, so we'll curve the point. We've done velocities and rates of change. Right now, we're going to work on techniques of differentiation. How to find the derivative of any function whatsoever. We're going to start working on that stuff. Are you ready for it? Trust me, you're ready for it. You're ready. If you can take a derivative, you're ready for it. Can you take a derivative?
Yeah.
You're ready for it. Do you want to do it? I don't know. You're ready for it.
Alright. That's the video for the day, I guess.